It's an honor to welcome you here, Seba.
Thank you, Rak, for the kind introduction. Thank you for the invitation to come here and the hospitality and for organizing this wonderful workshop. Let me say a few words before I start. This is intended to be a colloquium style talk. And on top of that, it's a colloquium style talk for, in principle, the Department of Mathematical Sciences. And this is what I had in mind when I prepared this talk. I know that there are a lot of people in the audience that are from our workshop, so I apologize if what I say is too simple for you. But on the other hand, when I attend colloquia, I hate when the colloquium is a technical talk or a seminar. So I prefer to have seminars and colloquia, not to call colloquia something that is a seminar. So that's what I had in. Okay. So because it is, let me tell you what this talk is not. So this talk is not a talk about what I'm most interested right now. Instead, it's a talk about some things that I consider interesting and that on top of that have been, in my research over a long time. Since this is a colloquium, I'm not going to go into too many details for those that are not experts, but I would be happy, I would consider this talk successful if by the end of the day, you have a flavor of some interesting stuff and you have questions that you might want to ask either myself, you can ask me while I'm here, or you can write to me, or you can ask Rak after I leave. That would be successful for me. Okay, but once again, I apologize for the physicists in the audience because some of the things might sound very simple. So I'm going to talk about the dialogue between physics and geometry, or physics and mathematics, and with an emphasis in some most recent versions of that dialogue. Okay, so of course physics and math have a long fruitful friendship and dialogue, and we know many examples of that through history. One of the most salient ones is the dialogue between mechanics and calculus. Newton wanted to apply his laws of motion and laws of gravity to describe, let's say, the motion of the planets. As here we see Principia, and he had to, in order to do that quantitatively, he had to develop calculus. It was also developed by Leibniz at the time, and it describes celestial objects. But since Newton in the 1600s, now calculus has applied to all branches of our lives. Another salient, very important example of this fruitful dialogue between mathematics and physics in both directions is the dialogue between Maxwell's equations of electromagnetism and vector calculus. All the ideas about gradients, curves, divergences, and so on play a crucial role in Maxwell's equations, which unified electricity and magnetism in those days, and predicted all kinds of interesting stuff, including electromagnetic waves or light, right? So we can say that, let there be light. More recently, if we move to the 1900s, when Einstein wanted to find a new way about thinking, to think about gravity, he borrowed ideas of Riemannian geometry, metric tensors, curvature, geodesics, and so on, to develop new ways of thinking about what we mean by gravity. And again, it led to all kinds of new and interesting things, like the understanding of black holes, gravitational lensing, cosmology, the history of the universe, and gravitational waves. And I would say that the dialogue is always in both directions. For example, in this example, you had to invent calculus, or Newton had to invent calculus, and so on. So there's some kind of a positive feedback between all these developments in physics and mathematics. There's another example that didn't fit into the slide, which is, of course, quantum mechanics and linear algebra. We are celebrating, first century of some of the first papers. Linear algebra was not something that physicists, now it's very common for us to think in those terms, but that was not something very common for the physicists at the time to think in that way. And actually, Heisenberg's paper, which was before Schrödinger's, was written precisely in that kind of a language. But in a language that became clear that was the language of linear algebra. So today, I'm going to talk about some other or more recent area in which this dialogue continues. And I picked it because it's the area that it's interesting to me, which is what we call quantum field theory. And quantum field theory underlines our description of nature nowadays in a variety of fronts. We talk about particle physics in terms of quantum field theory. We talk about condensed matter physics or the physics of materials in terms of quantum field theory. And we even talk about gravitation in terms of quantum field theory. So the talk today is about these two words, the word of physics and the word of mathematics. And here I listed a few of the topics that will be relevant for today's talk and also for tomorrow's talk. Hopefully you understand some of the, or you see some of the connections between these things that seem to be unrelated to each other at this point. So, on the side of physics, I will talk about quantum field theory, strongly coupled quantum field theories, maybe the Standard Model and its origin. We have in mind dualities, quantum gravity, and holography. And on the other side, with my mathematics, we might have things look like algebraic geometry, toric geometry, mirror symmetry, cluster algebras, combinatorics, integrable systems, or the Grassmannian. The colors here were randomly picked. It's not that I think that these topics are hotter than these topics, but what can we do? Had to be visually striking. Okay, very good. So again, here I apologize to my physics friends. So let me give an overview of some basic stuff about how we talk about particle physics, how we understand particle physics in physics. So in theoretical physics, we describe fundamental forces in terms of symmetry. So we associate the symmetry to some of the fundamental forces. And these symmetries are what we call local, which means that they can change from point to point in space-time. This is what we call gauge symmetries. And I bring this thing early on because I will mention the word gauge symmetry or gauge theory all along my presentation. So I want to get it out of the way so you know what I'm talking about. And if you forget about gravity, we're going to talk about the three other fundamental forces that we have in nature. One of them is electromagnetism. It's the first one after gravity that we always talk about. Is the one that is responsible for binding the atom together or the electrons to the nucleus. And the symmetry group in this case is U1. And it has one force carrier, which is the photon. Then there is another force, which is called the weak force or the weak nuclear force, which is responsible for radioactive decays, or the reactions in which protons become neutrons and neutrons become protons upon the release of some electron or positron and some neutrinos. The symmetry that we associate to that force, to the weak force, is SU2. And it has three force carriers that we call W plus, minus, and C bosons, C0. And there is a final one, another nuclear force. It's called the strong nuclear force, which is the one that is responsible for binding the quarks together, and on top of that, binding the nucleons together in the nucleus. And the symmetry in this case is SU3. And correspondingly, there are 8 force carriers, which are called gluons. This part, the part that talks about the strong force and the quarks in the Standard Model, is what we call quantum chromodynamics, or QCD, and I'm going to revisit that word later in my talk. And again, I refer to quantum field theories with these kind of symmetries as gauge theories. There is one of these theories that is the one that describes nature. And of course, physicists like to discuss the ones that don't describe nature too. But the one that describes nature is called the Standard Model of Particle Physics. And this slide summarizes its main ingredients. You have one field for each of these kind of particles. So let me go briefly over some of the properties of this thing. First of all, depending on the quantum behavior, these particles divide in two sets. There are some of them which are called bosons, and there are some other ones that are called fermions. So all the ones to the left of my hand here are fermions here, and all the ones here, which are the force carriers and the Higgs, are bosons. This is important to mention here because later I will talk about supersymmetry, which relates these two types of particles. And then we have the force carriers. We have W and C bosons. We have the photon. We have the gluons. Then we have things that are quarks, like up and down quark. These are the ingredients that form protons and neutrons. Have something that are called leptons, like the electron and the neutrino. All the physics in the periodic table is made out of this first column. But then the standard model comes with 3 copies or 3 families of the same type of particles. So we have cousins of those particles that are here, like the charm quark, strange quark, muon, mu neutrino, and so on, which have larger masses. So of course there are some questions about how to understand or why. Is there some explanation why we have these 3 families, and so on? And these are the kind of things that we would like to understand from a fundamental point of view in physics. So I wanted to explain a couple of things about quantum field theory. So I'll talk about gauge symmetries, that this is something that we like to do, or this is the language in which we like to talk about fundamental forces. I talk about one particular field theory that we like to talk about, which is the one which is responsible for our universe. And there is another thing that I want to discuss, that is the fact that we often like to look at, think about quantum field theories at different magnification scales. We like to zoom in or zoom out into quantum field theories, which is the same as looking at quantum field theories at different energy scales. Very high energies corresponds to very short distances, to very detailed description of your system. And zooming out or looking at things at larger length scales corresponds to going to low energies. Of course, when you talk about low energies, you have to say low energies compared to what, but something that I've been doing all the time is thinking about the low energy limit of things. Sometimes we talk about the low energy limit as the infrared limit and the high energy limit as the ultraviolet limit. And this process of zooming in and out and forgetting about unimportant details of the theory is called the renormalization group flow. And it's built in the modern way, or not so modern way, in which we think about quantum field theory nowadays, right? In the old days, certain theories were very problematic. People say, oh, these things are non-renormalizable or things like that. And now we think about them as this context as effective field theories that don't have any problem. They have to have some high energy completion and everything is fine. So things change with energy because of this renormalization group. And one of the things that might change is the strength of coupling or the strength of forces of the interactions that we are considering. They might become stronger, they might become weaker as we go to high or low energies. And one of the very interesting example that in its day was surprising, but nowadays is something that we think good behaved theories should have, is what's called asymptotic freedom of quantum chromodynamics. So here I'm plotting the inverse coupling or the inverse gauge coupling as a function of the log of the energy. And we see the coupling, the inverse coupling goes to 0. So the coupling grows at low energies. So this is was kind of unintuitive in those days, because what it means is that at long distances, the coupling grows. And one would expect that couplings decrease. One would have naively expected that couplings decrease with distance. But this is one of the reasons why quantum chromodynamics is a very difficult theory, and why so many efforts are devoted to understanding quantum chromodynamics or cousins of quantum chromodynamics, from which we can draw lessons about this real-world theory. From mathematicians, when you have a weakly coupled theory, you have some small parameter there, so you have perturbative methods to deal with them. When things are strongly coupled, you don't have a small parameter, so it's very difficult to deal with them. You can think about it like if you are doing a Taylor expansion, the expansion parameter is large, so there's no way you are going to have a good approximation by keeping a few terms. And in strongly coupled systems, well, the low energy or the long distance behavior might differ very much from the building blocks. So you might have something that microscopically, when you zoom in, looks like that. When you look from long distances, looks like something completely different. So that's something that happens in quantum field theory. So when you quartz grain, for example, you might start with quarks, and you might end up with protons, neutrons, and other stuff. So, but the main topic of today's talk is going to be the general thing of dualities. Or what do we mean by duality? So what do I mean by duality? For me, duality is going to be the following. It's that sometimes, and I will give you some examples, you might have two quantum field theories that look completely different, but nevertheless, they are equivalent. Okay? They might be fully equivalent, they might be equivalent in some energy regime, like low energies, and so on. So these two things are really indistinguishable. So you have to think about it as the same theory. From the point of view of the first slides, we might have different matter content. Imagine when I talked about the standard model, you might have different fields. You might have different gauge symmetries. You might have different interactions between them. So one of the things that the existence of dualities tells you is that this way of thinking about quantum field theories is not really fundamental. You shouldn't think that this is something fundamental. And sometimes duality is a very powerful tool, because it might, for example, map strongly coupled theories, which are theories in which calculations are very difficult, into weakly coupled theories in which calculations are trivial. Okay, so you might have a theory which you were hopeless to solve. Suddenly someone tells you that it's dual to something that is very trivial, and then you can use the dual to draw some interesting conclusions. So dualities are often discovered by rather indirect methods that involves knowing a lot about these quantum field theories. For the general audience, those methods don't say much. Just believe me that they involve a lot of intuition, putting together things like in some kind of detective work. So you talk about global symmetries, you talk about the formations of the theory, you might talk about some very detailed information given by certain indices, and so on. So it's very non-trivial to derive evidence for a duality or to figure out that the duality exists. And it's very important to emphasize that this is not a rewriting of the theory generically in terms of, it's not a change of variables, right? So it's something more fundamental. It's not that I will take theory one, I will make a trivial change, some complicated change of variables, and I will end up with theory two. sometimes it's a very indirect way of thinking about what a duality is. And it's a general phenomenon, right? So by now we know many examples of dualities in quantum field theory, different theories with supersymmetry, without, some cases without supersymmetry or with different amounts of supersymmetry in different dimensions, and so on. So one of the things that people are doing in the past many years is we are trying to chart the landscape of quantum field theories. So imagine that there is this is what quantum field theories can do, and there's some regions which are unknown to you, and we want to figure them out. Why? Because, well, you might learn some interesting stuff. You might learn, for example, that there's some exotic theory that does something that you didn't think it was possible, and then at a later stage, probably we discover that nature uses that mechanism. So we're also interested in thinking about quantum field theories in different dimensions. This has led to new ways of thinking about theories even in the dimensions that we care about, that are different from the general paradigm. We have extended our way of the kind of objects of theories that we like to think about. So we want to know what is the range of possible phenomena. We want to know whether there are surprises. There might be a surprise here. And from the point of view of today's talk, I will say that one possible way in which to investigate this landscape of theories is to use string theory to engineer these quantum field theories. I will show you what it means to engineer what does it mean to engineer a quantum field theory. And we will see that doing this provides new perspectives in the quantum field theory problem. However, I want to emphasize that the problems that we are discussing, nevertheless, are purely field theoretic, right? So I will use some realization of some quantum field theory in terms of string theory. I will use it to derive some conclusions. Nevertheless, those conclusions are going to be true regardless of whether string theory is the theory of the world or not. And today, I will focus on theories which are supersymmetric, which means that there is some symmetry between the bosons and fermions. And I will do that because it provides some additional control on the results. And we hope and we expect that sometimes we reach some conclusion in supersymmetric settings. Something like that still holds when there's no supersymmetry. For the non-experts in the audience, they won't be able to tell what is supersymmetric about what I'm doing, but that's what I want to say. Again, there are many motivations for supersymmetry. The strength of those motivations changes with time. It goes from things that have to do with particle physics or possible explanations about questions that we have about particle physics, and those motivations may or may not be decreasing with time. But nevertheless, what I want to emphasize is that from the point of view of today's talk, a supersymmetric quantum field theory is nothing else than the quantum field theory with, like the ones that we want to discuss, with some special symmetry, some additional symmetry. So it fits in the long tradition of the spherical cow, right? So nobody complains about the spherical cow, so we shouldn't complain about the supersymmetric cow either. Okay, very good. So, as I said, well, what I would do, how I will think about these quantum field theories in terms of string theory, I will use some things that are called branes, or D-branes. And string theory lives in 10 dimensions and contains some membrane-like objects which we call D-branes. So they come in different types. Again, I apologize for the physicists here, which have different numbers of space dimensions. They have one time dimension, but have different types of space dimensions. There are things that are zero-dimensional, zero space dimensions, so they look like points, like point particles. There are things that are one-dimensional in space, they look like strings. There are things that are three-dimensional, so they look like our world, and so on. So here, D pre-brane means that the number that is after the D is the number of space dimensions. So D3 brane is something that has three space dimensions and one time dimension like our world. So consider putting n of these three branes together in flat 10 dimensions. So we will have strings that end on these D branes. In some limit or at low energies, they will and when you decouple some of the other strings, this leads to a UN, so a theory, a quantum field theory with UN gauge symmetry. So it's a cousin of the field theories that we would like to understand, like the ones in the standard model. So this, on top of that, since we are considering these three branes, this looks like the three space and one time dimension of our world, so that's good. There are 6 transverse dimensions to this thing, which I cannot represent in the picture. And since I'm not doing anything to those dimensions, there's a rotational symmetry in those extra dimensions that is going to translate into some global symmetry of the quantum field theory. So what did I do so far? I put some branes together, I considered some limit, and I got a theory, which is a very symmetric version or a very symmetric relative of the quantum field theories that I'm interested in, like 4-dimensional UN gauge theory with a lot of symmetry. Okay, and I basically didn't do anything. I just put many branes together. So we say that quantum field theories arrive in the interior or what we call the world volume of these D branes. So now I would like to engineer quantum field theories in string theory, and I will give you 2 approaches to do that. One I will call brane tinker toys. Well, tinker toys used to be some toys for kids, and that one is going to be geometry. What do I mean by engineer? I mean designing or obtaining quantum field theories with some desired structure, which is more elaborate than the field theory that I just obtained before. And this is interesting because this can reveal some properties of these quantum field theories, as we will see. So how do I design quantum field theories first approach, or how do I engineer quantum field theories in the first approach? What do I mean by this brane tinker toys? So what I have to do is I have to combine different types of branes. So let's see what we do. So let me try to engineer super QCD. I talked about QCD, what's interesting. Super QCD, of course, it's super interesting. It's a QCD with supersymmetry. Okay, so it has a theory with quarks, gluons, maybe a more general group, and some supersymmetry in it. So I will do the same that I did before. Now I'm going to start representing things with fewer dimensions because I cannot put all of them in the screen. So imagine I have NC D4 branes. Before I had D3 branes, now I have D4 branes. So fine, I will have some theory which lives in 5 dimensions. We have some UN or SUN, I will say now, because the UN will disappear, but SUN gauge theory. So that looks good, it's promising. It's in the wrong dimension and with some general gauge group. And now I will cut them. And I will cut them, I will suspend these branes from some other branes, which are called NS5 branes. These are some 5 plus 1 dimensional objects that we have in string theory. Their details don't matter, but what matters is that they have a bigger tension or they're heavier than the D branes, so they serve as some scaffold or some structure of those D branes. Okay? Effectively, I cut or I made these D branes finite in one of the dimensions. So if I look at very large distances, much larger than this separation, I don't see this separation, and I only see 4. So I only see 4 dimensions at low energies. So I'm going in the right direction. That distance on top has a very interesting meaning. Right? It's interpreted as the inverse gauge coupling of the field theory. So if these things are very close, means a strong coupling. If they're far, means low, small coupling. And now I can start, it's a picture. I can start playing with the picture. I can tell my mom to play with the picture, and she will do the following thing. She will separate these things like that. So I started with some 3 brains that were together, and I separated them. And now I have some strings that are stretched between them that have a length. This is like a rubber band. It acquires some length, it acquires some energy, it corresponds to some mass. And this is a mass of a particle. And what I have just done is something that in physics is called the Higgs mechanism, right? Which is I gave mass to some of, in this case, W bosons. So these were W bosons of this thing. I gave them a mass. How did I get the mass? I gave the mass because there is some, in the Higgs mechanism, there is some field. In this case, it's an adjoint field that I gave an expectation value to. So there's existed a field there that corresponds to separating these things around, moving them around. That's the Higgs mechanism, okay? Which corresponds to the motion in the, well, here C direction means the vertical direction corresponds to that scalar. Very good. So we come back. So we already played like that. So I have QCD or something that looks like QCD in 4 dimensions. So we are good. So it's not QCD yet because we don't have quarks. We have to add the quarks, right? But first of all, it has this extra scalar that is not there in QCD. So what can we do is we rotate that other brain. So if I rotate that other brain, now my mom cannot separate these brains anymore. So I told you that separating those brains corresponding to give an expectation value to that scalar. So I effectively got rid of that scalar, or I gave it a very big mass. So the mass has to do with the tangent of that angle between these 2 brains. Very good. So we see that, playing with the brains that are around my brain, playing with the environment of the brain achieves interesting things. And we can imagine that the achievement of these interesting things is because I'm breaking the symmetry more and more, right? These things were parallel, now they're perpendicular to each other and so on. Very good. Here is a representation of where these brains live. There's going to be some 4 dimensions which are common to all these brains that are not represented here. And this corresponds to some of the other 10 dimensions. So we said that the most for the scalar is a relative angle. That's fine. And now we have to add quarks. So what we add is some other brains which terminate on some other type of brain. We call these 6 brains. And now we have strings that are not only stretching between these 2, but are stretching between this big brain and the brains that are responsible for the gauge group. And those things produce the quarks. What are the quarks? Are things, are fields that are charged under the gauge symmetry. So very good. In real life, these things have masses. So how do I give a mass? Again, you can imagine I just move this thing up and I force this string to stretch now, and that separation is proportional to the mass. So you see what the game is. So I produce these combinations of brains. Sometimes we call it brain setups. We call Hanani. Well, the original things like this were called Hanani-Witten setups. Now we call Hanani-Witten all these kind of setups. And I produce an interesting theory, okay, which is something that I'm very interested in, which is super QCD in 4 dimensions. I didn't do anything useful with it, but first of all, you got a flavor that many things get geometric here, motion of brains, distances, and things like that. I'm not going to discuss the dualities that this theory has, but it has some very interesting duality that corresponds to taking this brain here and just moving it around here. That's another motion that I can do. There is one interesting thing that happens when we do these things, that we shrink these brains. And I told you that this is corresponds to the inverse gauge coupling. And you can think that that duality will correspond to something like going through infinite gauge coupling, which is something that we are going to do later. Yes.
By internal dimension, there's 1 x and Say fine.
Sorry?
Can you explain more about the dimensions?
Oh, yeah. Well, it says here I'm representing everything by a line, right? But the blue things are default branes, so they have 5 dimensions. So I have to tell you where they are extended in. In this case, I'm going to extend it, and I'm going to number all the dimensions from 0 to 9, where 0 is time. So these guys are, and I'm not representing 4 of them, which are the interesting ones in which this theory lives. So this thing lives in 0, 1, 2, 3, and on top of those, that in the horizontal direction that I will call x6, or 6 dimensions. So there are 6 dimensions. 5 dimensions, sorry, there are 4 branes. Then the LS5 branes and the rotated LS5 branes are 6-dimensional objects. They are extending 0, 1, 2, 3. They have to extend in 2 more. You know, the vertical ones extending 4 and 5. The other ones extending like 8 and 9, and so on. So this is what this kind of diagram is representing. It's trying to give you an idea of where these things are extended. And I just kept the dimensions that are relevant for the discussion. Are you more questions? Yes.
Oh, okay. So 7.
Sorry?
7.
Oh yeah, 7 doesn't play a role today. Yes. It might play a role when you want to do things like crossing or things like that. Sometimes we might want to use the other dimensions that are. Yes. But in this configuration, so you're right. In this one, I didn't use. I'm just mentioning the ones that I use.
Is 5D or 4D?
No, at the end it's 4D. Why? Because the blue thing has a 5-dimensional work volume, and I cut off the work volume, and now I'm looking at low energies. So I'm zooming out, and this thing disappears for me. Very good questions. Okay. So this was the first way of playing with branes, with engineering quantum field theories in string theory. And now I will give you another one, which uses geometry. So, sorry, one of many ways of engineering quantum field theories, it's branes at singularities. Okay. So what do I mean? I want some quantum field theory has less symmetry and it's more structure, more intricate, and I want to achieve that. So let me show you how to do a 4-dimensional quantum field theory. So we come back to the original setup of many D3 branes. I told you on top of each other, there are 6 dimensions transverse to them. By the way, these things are infinite. We just show them like this, so they look like some page of a book or something like that. This leads to a very interesting quantum field theory, which is some people call it the harmonic oscillator of quantum field theory. It's called n equals to 4 super Young means. It's a very supersymmetric theory with many magical properties, but we might be interested in things that are not so symmetric, because the world is not so symmetric. So what we do is we might put these branes into something that is singular. That singularity or some pointy is going to break the branes a little bit and produce some additional structure. What you see is I'm doing with geometry what I used to do with branes in the previous slide. I'm playing with the ambient space and I'm breaking the symmetries with this thing. By the way, don't try to think about what are the dimensions here. It's this direction of the cone, the same direction of that. That's not what happens. These are the 6 transverse dimensions, which are in a 3 complex dimensional Calabi-Yau manifold. And the D3 branes extend in the directions of that we want our quantum field theory to be. So let's count the dimensions. So there are 6 there. This is 3 Calabi-Yau threefold. So there are 6 real dimensions. There are 3 plus 1 in the D brane in this example. So there are 10. Very good. So what happens if we zoom in close to the tip? Well, the branes are fractionized. We call it fractionized. So they split into different pieces, and the strings like to stretch between the pieces. What this is going to produce is there are going to be different, we call it gauge groups or different symmetry groups, very much like the standard model have 3 of them. The strings stretching between them are going to give rise to fields that are charged under different ones. different gauge groups, very much like the standard model. You know, this is 3 dimensions, 3 plus 1 dimension, so in principle it could be our word there. But I'm interested in these things more generally. So the structure of the quantum field theory that appears here has to do with the geometry of the extra dimensions. And we are interested in this map in both directions, right? I might be interested in what geometry produces certain quantum field theory, or what quantum field theory of given a quantum field theory, what geometry it corresponds to. And the geometry has the information or determines the structure of the quantum field theory. So you can say that the geometry gives you the DNA of the quantum field theory. Okay. And okay, the geometry determines the quantum field theory. That's a good one. Yeah. Very good. So this talk is, so we talk about quantum field theory in terms of branes and geometry. I said that I want to talk about duality today. How is duality going to appear in this kind of context? Typically, the way it manifests in this geometric realization of quantum field theory is that there's some single underlying geometric object. This is a picture of a Calabi-Yau manifold, but that doesn't matter. That has corresponds to 2 theories. Maybe there's some parameter here that I tune in some way, gives me this theory. I tune it in some other way, gives me some other quantum field theory. So that would be how what the manifestation of quantum field theory of quantum field theory duality would be in this kind of setup. But maybe I have a 3rd theory, or maybe I have a 4th theory or more, right? So what we will see is that the phenomenon of duality might be more general than 2. I will keep calling it duality, don't insist on giving it a different name, but it might be more general. So if you engineer quantum field theories by geometry and brane, I hope that this is the lesson that you get today. From here, first of all, we'll give you different intuition in these dualities, which is different from all this knowing all this detailed information about the quantum field theories and figuring out the duality. It suggests generalizations, and most importantly, it allows you for discovery of new dualities. So some dualities might be discovered in this way. So as an example, just in the second part of final part of this talk, just to give you an example of one incarnation of all these ideas, one that I was interested in for the past few years. I will talk about not 4-dimensional theories. I will talk about 2-dimensional quantum field theories. I will talk about Calabi-Yau fourfolds, and I will talk about something that replaces these tinker toys, these brane tinker toys, which is what we call brane brick models, which were mentioned very briefly in some of the talks. So I'm interested in 2-dimensional quantum field theories from branes and geometry. What do I do? Well, I do basically the same that I did before, but I changed the dimensions a little bit. So I put D1 branes at the tip of some Calabi-Yau fourfold. That's what I will do. And I will let the geometry of this thing generate some interesting structure there. These things are going to be special kind of Calabi-Yau fourfolds that are called toric. What they are doesn't matter, but one of the things that the toric Calabi-Yau fourfolds, the identity of this geometry that here are represented by a blue cone, but it has a lot of structure inside, is given by something that is some convex polytopes in some integer lattice in 3 dimensions. Okay, so if someone gives me this picture, it's telling me which cone I'm considering here. So a 2-dimensional quantum field theory will arise there in the D1 branes. So let me tell you a little bit about these quivers. We saw a few of them before. Normally, I will discuss a lot of these theories, but I'm not going to do it. Noshita said a few things about them. So the quantum field theories that arise here are described by quivers. For the mathematicians, a quiver is an oriented graph. They have some building blocks. The building blocks are going to be some nodes. that corresponds to what we call vector multiplets, which are meaning gauge symmetries. In this case would be UN gauge symmetries. There will be arrows between the nodes, or from one node to the self, that will correspond to bifundamental or adjoint fields. What it means here is that I have two gauge symmetries, gauge symmetry groups corresponding to these two nodes, and there is some field that transforms in the fundamental representation of one of the nodes and the anti-fundamental representation of the other node, very much like a quark can transform under SU3 and some other group, or SU3 and SU2 in the standard model. And there will be another type of field, which we call Fermi fields, which I will represent by a red line, very much like in the earlier talk, and I won't add an arrow for that because there's a symmetry of these theories that exchanges the Fermis with the conjugates. So from the point of view of an ordinary quantum field theory of the world that you know and love, each of these things are like electromagnetism or the strong force or the weak force, every node. And these things corresponds to the matter fields, the electrons and quarks and all these things. And this is an example of a quiver. It's just a representation of a theory which has 4 gauge groups and a lot of matter fields that are charged in different ways. And on top of that, there's something that we call the J and E terms that were mentioned earlier today, and some people call it a superpotential, or packages them in superpotential. Mathematicians like to call it a potential, or some people don't like to talk about them and say that this theory has relations that come from this potential. So this theory has potential. Potential or has to be gauge invariant in physics, so it has to be correspond to some closed loops. We will see there are some closed loops that involve one of the Fermis, not more than one of the Fermis. And if you look at this quiver, you will see that there are many, many closed loops that you can think about. However, the geometry will pick some of these loops. So this is not enough. If you want to tell me what this theory is, you have to tell me this information plus the potential. So you have to be able, if you start from the geometry, to determine both pieces of the puzzle, right? So this is half the identity of the theory. You need to know both. So the gauge theories that come from toric geometry, from cases in which the Calabi-Yau fourfold is toric, have a special structure that we studied long ago with Dongwook and with Rak. So that potential is such that every Fermi field participates in precisely 2 what we call J terms and 2 E terms. So let me tell you what it is. So this is an example of a geometry. We call it Q111. If you come to my talk tomorrow, I will talk about the same geometry. This is a quiver. It's the quiver that was there before. You have 6 Fermis here, 6 red lines. For each of them, you have 2 terms that close going in the direction of the Fermi, and 2 other terms that close going in the opposite direction of the Fermi, right? I didn't add the arrows here. I could have added the arrows like in Noshita's talk, but what I mean is that, if I call the guy here 1,4, well, this loop that sometimes I will call a plaquette goes through that Fermi field in the direction 4,1. So you see that every one of them participates in 2 terms. There could have been many more loops, and they would be totally fine from the point of view of a field theory, but the geometry picks, some of them. So here I represent, 1 Fermi. This is the same Fermi in all the cases, and we said that the Fermi participates in 2 plaquettes which are pink that go through the Fermi in one direction, and 2 other plaquettes which correspond to the E terms that go in the opposite direction. And this is the power I showcase my abilities with PowerPoint. Good. We can do it again. Very good. I can tell you when I went through small slides to big slides, they didn't coincide when they met together at the point. So we can play this game. Now we can combine them in such a way that this fact that they go through the same Fermi is kind of built in some kind of a graph. So in that way, we come up with what's called a periodic quiver, which is a quiver. I have nodes, have the arrows in the right places, and so on. But it's built in such a way that the way in which you glue things is that the plaquettes, the terms in the J and E terms correspond to minimal plaquettes here. What I mean by minimal, it's easier to see in the dual graph that I will introduce soon. But you can say that the smaller size plaquettes around the Fermi correspond to some of the terms that appear in the potential. So at this point, it's just a cool graphical gadget that contains the two pieces of information that I was talking about. It contains information about the quiver, it contains information about this potential or the J and E terms. It's just that. And we call it periodic because if you look here, this, I'm just giving you the picture for certain geometry, which have 8 gauge groups. And you see that all the corners are the same here, are identified. The 6 is also here, here, and here. So this thing lives actually on a 3-dimensional torus. Lives in a 3-dimensional torus. It's not a surprise. It has to do with some part of the global symmetry that comes from the fact that you are considering a toric Calabi-Yau 4-fold. Okay? So these are 3 of the U1s that come from the isometries of the Calabi-Yau 4-fold. All these things that I'm going to say, all these nice combinatorial structures are possible because the Calabi-Yau 4-fold is toric. Okay, so that's what. So it's general enough to see many kinds of theories with many behaviors that we would like to see, but it's constrained enough to give rise to some interesting combinatorial properties that we are going to exploit, and geometric properties. So what are brane brick models? These are honest brane configurations which are related to the D1 branes at the singularity by what we call T-duality, and that encode all the information that we want about the gauge theory, right? So this is a periodic quiver. This is, you don't recognize it, but this is related to the quiver that we have seen already in 2 talks. You saw this, that people were showing, if you forget about the framing node, a node with 4 black arrows and 3 red arrows. If you count here, you see that there are 6 red arrows and 8 black arrows, which is just twice that outcoming of this node. That's because this is the periodic quiver for that geometry or for an orbifold of that geometry. And the dual objects in which I replace lines by faces and so on is what we call a brane brick model. So, okay. The interesting thing is that this is indeed a brane configuration. You have to think about it as some 3-dimensional version of this Hanani-Witten setup that I was talking about at the beginning. So this faceted kind of surface represents some NS5 brane that is wrapping some geometry, and here you are seeing some like a limit of that geometry. Inside each of these bricks or balls in this case, or truncated octahedrons in this case, you have D4 branes that are filling the space. These are like the D4 branes that we have stretched in a segment before. Now they fill it. And the dictionary in the quantum field theory is that each of these bricks on the interior of this brick corresponds to a gauge group in the same way that the segment in the Hanani-Witten setup corresponded to a gauge group. These faces that I painted in black correspond to chiral fields. The red faces, which are all squares, correspond to Fermi fields. And every edge here that looks like a little book in which you have a red page and many black pages is one of these G and E terms plaquettes in the superpotential. Again, at this point, it will look like a lot of mental energy to draw this picture. The importance, and we don't solve things by drawing these pictures. We solve things by noticing that this structure is underlying what we do. So there are a lot of combinatorial properties of this object that translate in a lot of simplifications when dealing with the quantum field theory. So this is the original picture. some D1 branes at the cone, and the T duality turned into this. So the D1 branes here, the different fractions, fractional branes that we had here got translated into the D4 branes inside. The D1 branes get translated into the D4 branes inside these bricks. And this entire NS5 brane is the translation of the geometry to this picture. So these objects significantly simplify the connection between gauge theory and geometry. You can think that they are somewhere between the quantum field theory and that geometry. It allows you to read the gauge theory if you give me the geometry, or if you give me the geometry, I can construct this object and obtain the gauge theory. This is one of these things that you don't appreciate what you save unless you have suffered through it before. So believe me that it simplifies a lot of problems by considering this object. And again, that's the dictionary that I had before. Bricks corresponds to gauge group, oriented faces correspond to chiral fields, and oriented faces correspond to the Fermi fields, and edge corresponds to the plaquette in a J orbiter. Very good. So a number of years ago by now, Gade, Gukov, and Putrov discovered that there's a new infrared equivalence, a duality, for two-dimensional 0,2 theories. 0,2 means here some amount of supersymmetry, some little amount of supersymmetry. And it went like this. This is what we call two-dimensional super QCD. You have some gauge group, you have some global symmetry nodes, you can call it framing nodes, you can call it frozen nodes if you want. And they have different types of fields in it. And they realized that this is dual or equivalent to this other theory, in which you replace incoming arrows by outgoing arrows, or chirals that are charged in a certain way by Fermis by incoming arrows. Then you compose fields with the incoming arrow, and you form fields that give mass to this one. And you generate composition of these two fields into a new thing here. For those of you that are familiar with cyber duality in 4 dimensions, it's very similar to that. This kind of picture, which is the way in which it was given in that paper, is deceptively, it makes you lose perspective because it makes you think that this is just a rotation of the quiver, right? After some modifications of the ranks. It is not that. More generally, you just do this transformation in a general quiver, and it's a duality. The way these people found this is they were finding the Quivarian index for this thing. They were computing some complicated quantity for this thing, and they related that they realized this thing was symmetric under certain exchange of N1, N2, and N3. It's one of these non-trivial ways of finding a duality. But then they realized, so this is what we call a dual flavor, this is what we call a meson, some composite field. But then they realized that there's a third thing that is equivalent. And if you do a duality again, you come back to the original thing. That's why we call this thing triality. It's dual between 3 things. From the point of view of mathematics, and it's something that I will emphasize tomorrow, the interesting thing about this is that it's a new QR mutation of order 3. Of course, you have some generalized kind of a quiver where you have also these Fermis, and there is some nice operation that corresponds to a quantum field theory duality, which is a mutation of order 3. Of course, if you have more gauge groups, things are going to become more complicated and you have more rich. In this case, it will arise from the non-uniqueness of 2-dimensional 0,2 theories that come from a given Calabi-Yau fourfold. It's a very nice tool to study the dynamics of these theories. For example, you can determine whether a theory likes to break supersymmetry dynamically and things like that. And in terms of the brane brick model, it has some simple incarnation. You take one of these. If you have in your theory, in your brane brick model, a piece that looks like this cube, you take this cube and you do this kind of a cube move, and this is triality. Okay, so if you keep the rest of the brane brick model the same, and it gives you triality. A few things, these things that change color, these arrows connected to the node under consideration that change the color. are given by the fact that I rotated this cube in the middle a little bit. You see that the red faces are now at the front and back. Then I added these flaps, which corresponds to the composition of fields that appear here. And if you do this three times and you integrate out things that are massive, you will realize that you obtain the same theory again. And at the same time, this corresponds to keeping the Calabi-Yau fourfold the same. And once you start considering more complicated theories, the space of duals is really huge. So with Rak, we found one theory for each of these toric diagrams. This is a nice set of geometries. They're called the regular reflexive polytopes in 3 dimensions. And you have Calabi-Yau manifold for each of them, and you can find what the gauge theories are for each of them. So we find one for each of them, or one brain brick model for each of them. And then with my student Mario Carcamo, we constructed all the triality duals, or all the duals for all these theories, all these geometries. So you can see that, for example, model 18 looks pretty innocent here, has 831 different brain brick models, which means, right, so a few words. How this, by the way, this thing has only 12 gauge groups. Not all of them are this of the form of these cubes that will lead again after triality to one of these brain brick models. So it's many less than that that you can consider, but these things don't commute. These trialities on different nodes don't commute. So once you start playing, you generate 831. So it's very fast pace of duals. So here I represent how the duals are related for model 9. Model 9 only has 8 toric faces. So I call it toric faces, 8 brain brick models. But once you do a duality, you can obtain the same theory up to some permutation of the nodes and things like that. In this case, if you look at it, you get that there are 104 of them in this way. And this is entire, what we call a toric island in the duality web of this theory. Again, very beautiful structure that could be studied. Now, this is mega rich. And this one is nice. All of them are nice, but this one is nice because it came out with the symmetries automatically there. So,
this theory is generated by the triangle.
Sorry?
All the theory is generated by the triangle.
Yes. So this is triality restricted to remaining within the class that is declared by Blender.
Is it clear that it's finite?
Sorry?
Is it clear that the toric class is finite? When you do the duality, where the duality space is infinite.
Right. The number of toric faces is finite.
Yeah.
The number of duals is infinite.
Indeed, is there an argument why the number of toric faces is finite?
No. These are finite, and I don't know. I have never seen it for Calabi-Yau 3 was also to be infinite. Yeah, that's a good question. Of course, the duals are an infinite number. And I would love to see these numbers come out of like some geometric information here, and that's something that one can try to figure out. Very well. Do I have 5 more minutes? Yes. Very well. So I told you that brain realization produces triality as a cube move, this nice move. There's another way of thinking about triality from geometry and brains, which is using what's called mirror symmetry. The interesting thing is that you don't have to stick to Calabi-Yau 3-folds. You can do it for Calabi-Yau n-fold. So here you have toric diagram for some Calabi-Yau 3-fold, this toric diagram for some Calabi-Yau 4-fold. For each of these polytopes or toric diagrams, we associate what we call a Newton polynomial that is defined in the way that you can imagine, which is you have one monomial for each of these lattice points, where the exponents are given by the positions in the 3 directions. Each of them comes a priori with a complex coefficient. You can absorb n coefficients, sorry. you can absorb n-1 coefficients. In this case, you know, you're in Calabi-Yau fourfold. You have 5 points here. You can absorb 4 of the coefficients, set them to 1. You have 1 free coefficient, and so on. So this is the Newton polynomial. More generally, it will be some combination with complex coefficients. Those complex coefficients are important. That freedom will be reflected somewhere. And we can construct the mirror manifold, which is a double fibration over the complex plane of this sort. You know, this is the interesting part. You know, you have a fibration that is given by this Newton polynomial. Okay. So once you do that, you started from Calabi-Yau n-fold. In this talk, or most of this talk was Calabi-Yau fourfold, which was transferred to some d9-2 n branes. In this case, n was 4, was d1 branes. And the fractional branes become a collection of d9 - n branes wrapping some n spheres. So in our case, it's going to be d5 branes wrapping 4 spheres. So you see that every time that you change n by 1, you decrease the dimension of these branes by 1, and you increase the dimension of the spheres that they wrap by 1. So you change the dimension of the gauge theory by 2. This story was very nicely studied for Calabi-Yau threefolds in this paper. We studied with Sanmin and Rak and Kunrum for Calabi-Yau fourfolds. You know, in the mathematical literature, it was honestly studied before us by Futaki and Ueda in a very nice paper. So how do these things look like? They're very difficult to visualize, but we do something that's called tomography. So let me show you what it is, and I will show you how triality appears there, and that's going to be the end of my talk. So let me talk about this example. It has a name. It's called Q1 mod C2. You can see that this toric diagram, if you think about some triangulation in terms of tetrahedra, has 8 tetrahedra, or the volume is the volume of 8 tetrahedra. This means that, and I'm drawing things for some choices of the complex coefficients. So you see they have 7 points here. I set one of the points to 0, the one at the middle, and then I picked the coefficients in a very special way. You have some critical points on the W plane that represent like this. How many of them you have? You have as many as the volume of this toric diagram. Each of them is going to represent one of these collections of branes, which is going to correspond to a gauge group in the quiver. So how can I represent the geometry of this thing? What we do, what we call tomography, which is some kind of a slicing of these spheres on the X, Y, and Z plane. And you see that they look beautiful. They have intersections. So first of all, each line here or curve here of one color corresponds to one gauge group. In this picture, we have 8 of them. And there are intersections between them, and some matter fields are going to arise there. The arrows of the quiver are going to arise from them. Actually, you can even read the periodic quiver from properly projecting these pictures. Okay, so this has information about the J and E terms too. So what happens? How does the triality play appear here? Well, I represented this for a given set of coefficients. What happens if I change, and I can predict, I can calculate a quiver. What happens if I change the coefficients such that I do the following thing? I take this yellow sphere that I call gamma 1, that corresponds to node 1 in my quiver. No, node 1 here, node 1 here. And I move it past some other branes in some very specific way, or you can think that I shrink it and let it grow again somewhere else. So this is what we call this is a geometric transition in the mirror. So if you look at the order on the W plane, the only thing that I did is I changed the order of gamma 1, move it here. But you see that all the other sphere, all the other projections of the spheres change, and the intersection change. And it changed in a very special way, which is, it gives rise to this periodic quiver, which is indeed a triality dual by a duality on node 1. So you can think that in the mirror, we are really doing the same thing that I told you before. We are going through infinite coupling by shrinking this guy and then sending it to making it grow somewhere else. So it's very similar to what we were doing in these Tinker toys. And the freedom of these complex coefficients is what is the manifestation here of triality. By the way, after that, this way of thinking allows us to predict another duality of order 4 for 0 dimensions, and you can extend this for Calabi-Yau n-folds and so on. So, this geometric way of thinking unifies dualities that look different and allow you to generalize in a very simple way. So what are the conclusions? I hope that I convinced you that there's some exciting dialogue between modern theoretical physics and mathematics and geometry. I only explore one corner of it. I talked about the corner that's closer to my interests. Embedding quantum field theories in string theory using brains and/or geometry is a powerful tool for studying the dynamics of these theories. This approach often provides new perspectives on the quantum field theories, which are geometric. You see things in a way that is sometimes quite intuitive. And conversely, geometry gives you a lot of ideas about mathematics, about physics, but I also think that physics gives you nice ideas about mathematics. There are other examples nowadays that people are very interested in. There's a whole lot of mathematicians and areas of mathematics that are pushed by their interest coming from physics. Amplitude-hedron, cluster algebras, positive geometry is one example of that. Duality is one of the most fascinating and conceptually deep phenomena in physics, and geometry leads to profound understanding and discoveries, including the unification of dualities that look very different from each other. I think it's interesting to look forward to see what surprises this marriage or this friendship can bring in the future. Okay, so thank you.
Thank you very much for the very exciting talk, Silva. Any questions in the audience? Yes, Silva?
So if you go to, say, the 4-dimensional dualities, like cycle dualities,
Yes,
they can also be regarded as kind of geometric fields.
Yes. Yes, so that was exactly the idea. So when we were writing this paper, we know how it looks for cyber duality. Come from me 2 seconds, says, okay, we have to do it for Calabi-Yau 5-fold. What you have is, so these things have an order, cyclic order. It has to do with the grading of the fields. So here you can divide things into 3 wedges if you want in the plane. It has to do with those other spheres that provide incoming chirals or Fermis or outgoing chirals to this node. They're all in very specific order. Then you just move them through the incoming chirals. On the inverse reality, will be moving through the outgoing chirals. In the case of cyber duality, you divide the plane only on 2 halves. There are incoming chirals and outgoing chirals. So that's where the order of the duality comes from.
Now, do you also have some analogous statements for the 3-dimensional theories and 5-dimensional theories? I think, for the 3-dimensional theories, we have this, the brain cycles.
With shared cycles.
Yeah.
Yeah. I think that one can do something like that. Yeah.
Though the geometry changed, there's no difference between quivers, right?
Oh no, the quivers are very different. Yeah, if you count the number of fields, they look similar here, but they're very different.
Yeah.
I should draw the ordinary quiver here. Still, they're very different. And the giant eaters are very different. They're very.
Any other questions? If not, let's thank Seba again for the